I'm Georgy Kucherin, and I work at Kaspersky Grade. And you may have heard about my research about APTs like Lazarus, Turla, APT41, operation triangulation, and many others. And if you, just like I, are doing reverse engineering on a daily basis, then you know that threat actors can turn the process of analyzing malware into a nightmare by using obfuscation. And this applies to all types of analysis. Well, if you decide to read the code, if you decide to use static analysis, you may find that the code is unreadable. Well, you may want to circumvent this and try to run the malware in a sandbox or a VM and thus use dynamic analysis. However, advanced malware can implement sophisticated anti-VM or anti-sandbox techniques which may prevent the malware from running. And in order to be able to launch the malware, you will need to understand how these techniques work. You need to read the code that implements them, and you're not able to do it because the code is obfuscated. When it comes to dealing with obfuscation or packing, there are some methods that you can use. For example, you can identify the obfuscator used, and you can search Google for a tool that will do everything for you. And another way is to try to launch the malware and try to dump its process at a lucky time, hoping to find unpacked code there. However, advanced actors, they know all these generic methods very well. And if they don't want their samples to be reverse engineered, they do their best to implement techniques that are very hard to beat. And I and principal security researcher Sergey Belov, who is also working at Kaspersky and who is my mentor, we were once analyzing a sample of an APT called FinSpy or FinFisher. It has been in discussion for more than 10 years in papers. And when we got the sample, the first thing we decided to do is to open it in IDA. And I think we should open it in IDA too, because right here I have a virtual machine prepared for demonstrations. So if we open it in IDA, well, the first thing which you can see is this navigator bar right here. Notice that it is mostly gray. So if you go outside in London on a very rainy and depressing day, and if you look above in the sky, you will see the same gray color. And so for unobfuscated samples, this color, it should be mostly blue. But this one is gray, and so this means that the analysis of the sample is going to be very depressing. Okay. Up next. This is the win main function, like the main function of this binary. And its address is colored red. So if it's colored red, this means that IDA failed to create a function at this address. Now we need to find out why this is happening. And to do this, let's read the code of this function. So it starts pretty much with generic code. The function prologue, push EBP, move EBP ESP, sub ESP something. That's pretty standard for a function. But then what we see is a jump if zero instruction. This instruction makes a jump if the zero flag is set to true. And before this jump if zero instruction, we have an XOR EDX EDX. So this instruction sets the value of EDX to 0. And by doing that, it in turn sets the zero flag to true. And so, although we have a conditional jump right here, it will be executed. It will be taken, no matter what. Now, let's take this jump. And over here, we see instructions that are separated by pairs of jumps. Let's take a look at the first jump that you see on the very top of the screen. Now, we see that those jumps, those two jumps, they lead to the same address. And what we also notice is that those jumps are opposite to each other. Here, jump if 0 and jump if not 0. This pattern is repeated for all other jumps that we see. And what we can do is we can simply replace those pairs of jumps with a single conditional jumps, because no matter what, one of these jumps will always be taken. We can do this with either Python, and luckily, we do not need to implement this from scratch because there is a script from a researcher, Rolf Rolls, that already does this. All we have to do is to paste this plugin, its contents into the plugins folder, and you're good to go. Now, when we run this plugin, IDA will be able to create a function, and the address we saw earlier will no longer be read. And the function that we will see, it will be very large. It doesn't fit on the screen. Here is a snippet of it. And if you analyze it, you'll eventually find out that it decrypts and decompresses a blob of data. Let's look at this data. So it consists of byte arrays of size 24. And whenever you see such byte arrays, what you can do, you can try to search for patterns in them. Here we can find this pattern. The fifth byte of each byte array is a small number. If we look further, we'll find out that this number is used to index this array of functions. It has 34 functions. And let's take a brief look at them. Those functions, as you can see, they are very, very small. This one, and this one. And if we keep analyzing all those 34 instructions, we'll find out that they emulate an entire computer architecture. So what the threat actor did is that they took x86 code of their malware, then invented some custom exotic computer architecture, and converted the x86 code to this architecture. And those byte arrays that we saw before, they are actually instructions of the virtual architecture. And these functions, each of these functions is responsible for emulating one of those instructions. In order to understand what is happening in this sample, we need to be able to transform those virtual instruction bytes to something sensible. So what we have, imagine like you are trying to reverse engineer a .NET or a Java sample. Java and .NET, they also rely on bytecode, but imagine you do not know anything about the language internals. You do not have a disassembler. You do not have a decompiler. You are all alone. And you have to make something sensible out of those bytes. Now, of course, this obfuscation is not novel. It has been discussed before. But if you make a Google search, like Google virtual machine deobfuscation, you will find a lot of tools that are complex. And some of these tools even use academic level techniques such as symbolic execution. So when I saw that, I decided to write my own tool. And what I also wanted to do, well, the tools that I saw, they were external frameworks that contain like a known disassembler, a known optimizer, and stuff. So what I wanted to do, I wanted to resort just to IDA and the Hex Rays Decompiler, the two tools that every reverse engineer knows. So before doing any scripting, I decided to take a look at the virtual instructions. Having reverse engineered all the 34 instructions, it became clear that all the instructions can be divided into three types. The first type of instruction is a jump instructions. So right here on the screen, you see this function, and it takes a value of the E flags register. And now note, right here, second line, we apply bit masks to it. Flag 0x40 and 0x1. Those bit masks are used to check whether bits of the E flags register are set to true or false. And to do this, we need to find out what those constants mean in order to find out what this function is doing. To do this, we can consult the Intel architecture manual, the documentation of the E flags register. From it, we're able to find that 0x40 is 0 flag, and 0x1 is carry flag. And so we have a condition. If 0 flag is not 0, or carry flag is not 0. To find out what this condition means, we can consult the same manual. So we have various conditional jumps in Intel architecture, and by consulting this table, we can find out that this is a jump if above instruction. Now, there are more instructions of the same type, like here, for example. Here's one comparison, jump if not 0, and this one is jump overflow. Now, there is a second type of instructions. They perform various calculations, and they make use of a virtual register. On x86, we have 8 general-purpose registers: EAX, EBX, ECX, EDX, and so on. But this architecture has only one virtual register. Here is an instruction that adds a number to a virtual register. There are similar instructions, like shift the virtual register value left, or right here, dereference the virtual register. And finally, there is a third type of instructions. This third type simply executes native x86 code. Please pay attention to those instructions on the screen. Right here, for the first instruction, you see it contains byte 60. The byte 60 corresponds to the push AD instruction. And the second instruction, 33C9, and this is XOR ECX ECX. So just native code encoded in virtual instruction operands. Now, you may have noticed that the instructions that we have discussed, there are equivalents in the x86 architecture of those instructions, like jump if above, shift left, add, and so on. So what comes to mind is that we can try to translate the virtual bytecode back into x86. And we can then import this bytecode into IDA and analyze it. Now, we have 3 types of instructions. We just discussed instructions that execute native x86 code. Those do not need any translations because the native instructions are already encoded in the operands. Now, we have also jump instructions. Well, a jump if above in a virtual architecture is the same jump if above in x86. So the second type is also easy. There are equivalents of those instructions. And we are left with one type of instructions, those that perform calculations with the virtual register. And as it turns out, translation of these instructions is not really a straightforward task. To show that, let's look at this instruction. This is a virtual instruction. It shifts left the value in the virtual register left by 3 bits. Now, to translate this instruction to x86, we need to find out where to store this virtual register value. So if you have an x86 computer, we can do it in 2 ways. The first way is to allocate a register, an x86 register, and say, for example, that virtual register will be stored in EAX. And the second option is to place this virtual register somewhere in global memory as a global variable. And in this case, the shift left instruction will contain a dereference operation. So what should we choose? Should we choose the register option or the memory option? To discuss this, let's look at the following code. It's virtual code that contains 3 lines. The first instruction executes native code. It moves the number 3 to EAX. The second one moves the value 400300 to the virtual register. And the third instruction, it moves the value in EAX to the address stored in the virtual register. Effectively, those 3 instructions move the number 3 to the address 400300. And now, let's try to stick with the first option. Let's replace the virtual register with EAX. In case of the first instruction, as I said, we do not need to perform any translations. We just copy the x86 code in the operands. It's move EAX3. Now, the next instruction, move virtual register 400300. We replace the virtual register with EAX. it becomes move EAX 400300. For the last instruction, we perform the replacement of virtual register to EAX again. So move D word at EAX, we move it, the value stored in EAX. And now let's execute this code and see what results we have. The first instruction moves 3 to EAX. And the second instruction immediately overwrites this value with 400300. And the third value moves the value in EAX, which is 400300, to the 400300 address. And so at the end, we have the number 400300 stored at the address. But we should have stored the number 3. So this is a contradiction. The translation contains a mistake. And thus, this option of replacing the virtual register with a real one is not good for us. Thus, we're left with a second option, to store the virtual register in memory. I'll show you further how it looks like. But for now, let's try to translate those instructions that we have to x86. So the shift left will look like this. We replace the virtual register with a dereference. For example, for the instruction that adds a value to the virtual register, we do pretty much the same. Also include a dereference because the virtual register is stored in memory. But it's not really straightforward for all such instructions. Let's take, for example, this instruction that dereferences the value in the virtual register. So if you were to translate it to x86, we would need something like a double dereference, because we first take the value of the register and then we dereference the address at it. But on the x86 architecture, we cannot do stuff like this. On x86, I'll remind you, it is possible to move contents of memory to a register, and vice versa. We can move register to memory, but we cannot move memory to memory. And thus, we have to translate this instruction, this virtual instruction, into many x86 instructions. So the first thing we can do, we can move the value of the virtual register, which contains an address, to EAX. We then dereference EAX, obtaining the value stored at this address. And we put the dereferenced value back to the virtual register. But here we're using a register called EAX. And if we just leave this as is, we can lose the value stored in EAX. That is why we should surround this code with a push EAX to save the value on the stack. And then at the end, we place pop EAX. We pop the value of the stack. And now, in the same way, we perform translations of all the 34 instructions. It just requires basic knowledge of assembly, and that's it. And once we have done this, we can write the translations to our IDA database. The process of writing is also really straightforward. Passing of each instruction does not take more than 10 lines. We just assemble the instructions into bytes, and that's it. And now let me show you how this works. So, File, and I click Script command, and here is the script. It's like 219 lines along with comments. And now let me increase the size of the navigator bar, and let me try to run the script. I run it, and notice how this bar gets populated with brown. So brown here means instruction. It gets populated with instructions, and IDA is doing auto-analysis. So now what we can do, let me close this window and minimize the bar. And if we choose the list of segments, here the script creates a segment called FinVM. I'll show you how it looks like. So at the start of this segment, we have a variable, a D word, called virtual register. So notice I told you that we are going to store the virtual register in memory. So that's the place where we store it. We create a new segment, and we store it there. And if we look down, we see the translations of instructions. Like here, push A, that was an instruction that executed native code, and the knobs are used for padding. Now next, XOR, ECX, ECX. Now sub ECX, some number, move virtual register something, ECX. And so we have translations here. And once we do this, once we write the translated bytes, what we can do we can head to the winMain function, and here I press the P button to define a function. And now, let me decompile it. I press F5 to do this. And now let's look at the results. If we scroll down, right here we see a call to an imported WinAPI function, global alloc. Now we scroll down, and here we see a string. And this code pretty much looks like deobfuscated code, but there is a problem. Take a look at lines 94, 95, and 96. Right here, we set the virtual register value to 1. Then we call the setErrorMode function, and then we immediately override the virtual register variable with this v44 variable. Now, this assignment, we do not need it. So our code contains assignments that we don't need. And if we scroll upper, I'll demonstrate the size of the problem. There are a lot of these assignments, and they make it very difficult to read the code. And we need to do something to improve the decompilation. Now, of course, the Hex Rays Decompiler includes optimizations routines for those dead moves, but it turns out that the Hex Rays Decompiler does not perform optimizations on global variables, and virtual register, as I have said, it's a global variable. And we have to do something with the decompilation to fix this stuff. And so we have to study the internals of IDA's decompiler to find out how to do this. And it turns out when you click F5, when you translate assembly code to C with a Hex Rays Decompiler, the decompiler transforms assembly into an intermediate language called the Microcode. Well, you can see this microcode on the screen. I view it with a plugin called Lucid, and this microcode is pretty similar to assembly. And to the right, you see this thing, mmat generated, mmat pre-optimized, mmat lookup, and stuff like this. These things are called maturity levels. So the higher the maturity level is, the more optimized the code looks like. And what we can also do, we can represent each microcode instruction in the form of a graph. Right here, you see an instruction that moves the number 1 to virtual register. It is one of the assignments that we need to remove. It consists of 2 operands. The first operand is a constant 1. MOPN means number. And the second one, MOPV, variable. It is the virtual register variable. So what we can do is try to tell IDA that this variable should be optimized. And we need to replace this variable with some kind of object that is optimizable. Now, if you browse through the documentation of the Hex Rays Decompiler, you will see that it contains an object called a kernel register. Well, on x86, there are kernel registers, or there are registers like EAX, EBX, and so on. I already told you today. But if you are working with microcode, you can define any number of registers as you like. And these are called kernel registers. So what you can do, we can tell IDA to treat this virtual register variable as a kernel register. Now, the process of doing this is not really straightforward, but I'll try to explain you the basics. So the first thing we need to do, we need to register a so-called decompiler hook. Now, it's very easy. It's just a function that gets invoked whenever we press F5. And now this function is on the screen. Let me explain you what happens here. So first of all, we take the first argument of the function and store it in a variable called MBA. Now, if you Google MBA, you'll find out Master of Business Administration, but it's not. MBA is called micro block array. It's an object where the microcode is basically stored. Now, what I do next, I allocate the kernel register, the one I told you about. And then I invoke this forAllOps method. Now, this method allows us to iterate over all operands of all microcode instructions. And it allows us to perform some action with those operands. This operand replacer class, which you see on the screen, it performs those actions. Let's look at the contents of this class. In it, we perform a comparison of the operand which we are iterating over. We check if its type is MOPV and whether it's a virtual register by comparing the address of the variable. Now, let me show you again. This operand that we need to work on, red, it has type MOPV, and its value is the virtual register. And if we meet such operand, we invoke the makeReg method, and we replace it with a kernel register. And if we run it, we'll see this. Now notice that the type has changed to MOPR. R means register. And what we see in the value is KR00. KR means kernel register. Now let's see if it helps. I'll open IDA, file, script command. I again run another script that I have here. And once we do it, we go back to the vim main function, and let's see if it helped. So if we scroll down, we see that there is no more mention of the virtual register variable. And the same code that I showed you before with set error mode, it no longer displays those assignments that are redundant. And so if we look at the decompilation in general, we'll see that it's pretty much good-looking code. This is, for example, a stack string, A, V, C, U, F, etc. So a lot of stack strings. So it's pretty much unobfuscated code. It is like the same as if there were no virtualization at all. And this means that we have successfully completed our task, and we have devirtualized the malware. And so devirtualization is a very complex task to handle. And what we used IDA and Hex Rays Decompiler, those two tasks, those two programs, the IDA and Hex Rays, they contain a really good API. If you master it, then you'll be able to save a lot of time on writing frameworks. You can just use the API for interacting with disassembly and the decompilation, and you'll be able to do whatever you want. And also note that the code is less than 250 lines long. Like, if you stop papers on devirtualization, you'll find out thousands of lines of code. But this one is just 240. This is all thanks to the features of IDA and Hex Rays. I published this code on GitHub, and I encourage you to check it out. I encourage you to download the sample and to run this code step by step. And if you encounter any problems with it, you can contact me, and I'll try to help you. And if you have any questions right now, please don't hesitate to ask them. Thank you.